Hello brainy folks, it's me again DanielAryee, welcome back. In today's tutorials, I will break down how the oscillatory behavior, or the evolution of all possible locations of an electron in an atom at a given position or point can be measured and calculated through the use of Euler's equation, thus e raised to power I multiplied by pi plus 1 is equal to 0, in the exciting field of quantum physics. Alright, let's go! Yes, in quantum mechanics, Euler's equation is used to describe the probability of a particle's wave function. So how does it work? Alright, let's consider for instance this typical scenario, where we would want to calculate the probabilities of the various possible locations of an electron in an atom. Here the answer to such cases is determined or given by calculating the probability amplitude of the particle's wave function. Here the specific particle under consideration is the electron, and in the process of doing that, the wave function is expressed in an exponential form and subsequently evaluated as a trigonometric functions by using Euler's formula towards finding the solution. In other words, these kinds of questions can be solved by using this mathematical formula, psi of x equals e raised to the power open bracket I multiplied by the product of k and x, bracket closed, where x refers to the point or position of the particle and k refers to the wave number, in addition to subsequently breaking it down into a trigonometric function using Euler's formula. Thus psi of x equals e raised to the power I times k times x, and this is equivalent to e raised to the power I multiplied by theta, which by extension can also be expressed as cos theta plus I multiplied by sin theta, towards finding the solution, where theta in this case equals the product of the wave number and the particle's position kx. Good. Now in order to solidify your understanding, please consider this practical example below. Determination of the probability amplitude in quantum physics by DanielAryee, December 21st, 2024. Question: a particle's wave function is described by the formula psi of x is equal to e raised to the power open bracket I times k times x bracket closed, where k is equal to 2. Now calculate the probability amplitude for the particle at position or point x equals 1. Great, here we have to use the formula psi of x equals e raised to the power open bracket I multiplied by k times x bracket closed and the corresponding trigonometric function by incorporating Euler's formula, etc. in order to calculate the probability amplitude for this particle at position x equals 1. Sure, so solution step 1, substituting x equals 1 and k equals 2 into the formula, gives the following result. Thus psi of 1 is equal to e raised to the power bracket open I times 2 multiplied by 1 bracket closed. Hence by mathematical manipulation, psi of 1 becomes e raised to the power I multiplied by 2. Alright, great, let's move on to the next solution step, and to do that we would have to transform the result of psi of 1, thus the complex exponentials, into a trigonometric functions by evaluating it in the context of Euler's formula. At this point it is equally important to note that the wave equation or the trigonometric function is key, because essentially we are seeking to calculate the probability amplitude of the electron's wave function at position x equals 1 given its oscillations. Alright, so let's get the ball rolling. So solution step 2, evaluate the exponential above using Euler's formula. Okay, here because we know that e raised to the power I multiplied by theta is equal to cos theta plus I multiplied by sin theta gives rise to the situation where the result in solution step 1 can be rewritten as e raised to the power I multiplied by 2 is equal to the cosine of 2 plus I multiplied by sine of 2. Hence by implication, this is mathematically the same as psi of x equals cosine of 2 plus sine of 2, since psi of x must be equal to e raised to the power I multiplied by 2. Great, now let's move to the next solution step. So solution step 3, here we will have to calculate the probability amplitude of the wave function above by using this formula. Thus psi of 1 equals the square root of re of psi squared plus m of psi squared. Here re represent the real part of psi and m represent the imaginary components of psi. Therefore by comparing to psi of 1 in solution step 2, it is clear that the re equals cosine of 2 and the m is sine of 2, therefore after substitution into the stated probability amplitude formula above, each of these components will be squared accordingly and appropriately by the Pythagorean pattern. Good, so now that you have a better understanding, let's quickly do the mathematical manipulations. So probability amplitude of psi of 1, or what you can also be called as the magnitude of psi of 1, equals the square root of the cosine squared of 2 plus sine squared of 2. This reduces to the answer of 1. Okay, here, Let me quickly explain further. Yes, get this catch, thus you must learn to use trigonometrical identities at this stage before proceeding with the mathematical computation. Hence, given the terms and the pattern of the wave function in the probability amplitude formula, at this current state of the solution, it could clearly be seen that the wave function mimics the Pythagorean trigonometrical identity after doing some comparison. Thus, specifically in this case, I am referring to sine squared of x plus cosine squared of x equals 1. Therefore, by substitution of this trigonometrical identity into the amplitude formula, the probability amplitude of psi as a function of point x equals 1 now reduces to square root of 1. In other words, the magnitude of psi of 1 is unitary. Good. After further mathematical computation, we end up with the answer or solution to the question above, and specifically we can now state that the probability amplitude of the particle's wave function at position x equals 1 after all mathematical computation and manipulations is 1. Yes, the final answer is 1. Wow, now you see, very elegant, isn't it? Ha, ha. Alright, before you exit this tutorial, let me further substantiate the teachings above with the following fact and truths, in order to reinforce your understanding regarding the underlying concepts and mechanics of the solution. Alright, great, for a better assimilation. Here are a few facts to retain in memory. Thus, 1. Indeed, transforming the exponential function into its trigonometric form, using Euler's formula, where e raised to the power I multiplied k times x becomes cosine of kx plus I multiplied by sine of kx, has this significance that must be observed. Thus here it must be noted that kx is equals theta, thus the product of the wave number and the particle's position equals the angle of theta. And in this case, that value is 2. Right, get the catch here. Breaking it down this way connects the wave function to oscillations and makes it easier to calculate measurable quantities like the probability amplitude, which depends on the real and imaginary parts of the oscillatory behavior of the wave function. Truly, by extension, this is one of the most profound reasons why Euler equations remain so powerful and useful in the domain of physics, engineering, and mathematics, especially in quantum mechanics, where wave phenomena are very prevalent, critical, and foundational. Yes, its power lies in its ability to connect exponential and trigonometric functions. 2. Okay, now let's consider the interpretation of the probability amplitude, which indicates the likelihood of the particle being found at position x equals 1. Thus, the probability amplitude equaling 1 from the calculations above suggests that the wave function's oscillations are normalized to unity. This means that the probability distribution density of the particle is uniform, indicating that the electron's presence or location is equally likely distributed with a uniform or constant probability across all x in this case. However, if the probability amplitude were say 0.5 or 0.8, it would indicate a lower likelihood of finding the particle at position x equals 1, and by extension it will also mean that the underlying probability distribution is not uniform anymore. Please remember this could occur if the wave function is modified, for instance through the introduction of a damping factor or by changing the normalization. 3. Alright, now let me throw a little bit of light on the parameter k, which is also called or referred as the wave number. Indeed, the wave number describes the spatial frequency of the wave function. It is related to the wavelength mathematically by the formula below. Wavelength, also known as lambda, equals 2 multiplied by pi all divided by k. Therefore, because k equals 2 in the question above, it implies that the wavelength lambda equals pi, thus after substitution. 4. Great, let me also break down and do some quick interpretation of the amplitude formula. Thus specifically the Re and m in the formula represents the real part of the wave function and the associated imaginary part of the wave function. These components allow us to compute the magnitude of the wave function, which is the probability amplitude. In other words, the formula helped us to calculate for the probability amplitude given the oscillations of that quantum particle at a particular point or position, in this case exactly at point x equals 1. 5. Okay, now it is time for me to take you through the interpretation of the associated graph I have provided based on the wave function in the question and the corresponding calculations, in order for you to appreciate the evolution of the oscillation behavior of the quantum particle and other complementary details. Alright, let's get in. Yes, first of all, in this graph there is a clear display of the real and imaginary parts of the wave function, which has been differentiated or distinguished by color. Specifically, the blue curve shows the real part and the orange curve shows the imaginary part. In addition, The red dashed line indicates where the probability amplitude was calculated, thus exactly at point x equals 1. 6. Now here is the last kicker or hint, thus you should take theta to be equivalent to x, which in turn is determined or equivalent as k multiplied by x. Yes, by both calculation and observation, we have the value of 2 in this case. In other words, the product of the wave number and the particle's position is the angle in the trigonometric function, and in this context it describes the oscillations or wave-like behavior, with kx being the spatial phase. Once again, I am DanielAryee, thanks for watching, and please do not forget to like, share and subscribe to my channel at DTechnology4 for more exciting and enlightening series, where I would take you through various extensions and calculations in the fields of electrical and telecommunication engineering, specifically Fourier analysis and signal processing, even up to extent of attenuation optimization. Yes, it promises to be very exciting and possibly more challenging, since it may involve some of methods in Fourier analysis, which is somewhat more complex than the single pure wave function or the monochromatic wave function encountered in this tutorial, because it has to do with breaking down a wave packet involving superimposition of multiple waves into sinusoidal components. Great. To this end, I hope you will agree with me that assignments can increase retention, reinforcement, and even help you build problem-solving skills. Hence, please consider working on the same problem as above, but this time both k and x have the same value, specifically k equals 2 and x equals 2. Kindly let me know your results or comments to this assignment at the comment section below. As usual, keep expanding the frontiers of your knowledge and never stop learning. See you in the next video. Take care. Bye.